Okay.
Hello, everyone. Today, I will start introducing this lab. I will try to explain more or less the dynamic of the lab. Can everybody hear me, by the way?
Yes.
Okay, good. So the basic dynamic, okay, so this is going to be the first time that we tried it, which is basically due to the current circumstances. We didn't plan for this at the beginning. We wanted more to be kind of a hybrid thing and in presence, but given the current circumstances, this is the best that we could do. So Zoom has a feature in which we can create something called breakout rooms. And the idea is that usually lab sessions are done in groups, right? We encourage to work in groups because it's easier, and then there might be some students that are better at certain topics and have certain skills that others don't have. So the idea is that we encourage this collaboration. So we're gonna make these breakout rooms with groups of 2 or 3 people. And the idea is that Michele, it's going to, Professor Michele is going to explain the first exercise, which is basically about modeling. The first thing that we need that you guys need to do is go to the Moodle of the course and download the files that have been just posted in an announcement. And once you've downloaded the files, you will see a PDF with the description of the lab. And the lab is divided in 2 parts. One part about modeling, which is, so the whole idea of the lab is that we're going to do modeling and control of a DC motor using MATLAB and Simulink, mostly Simulink. As we already explained, it has a lot of features when dealing with system modeling, with control, and it has a lot of useful already built-in tools that are good for design and analysis. So the first exercise, which is M1, Professor Foki is going to explain it first. And then we're going to allow you we're going to create the breakout rooms, and then we're going to let you try to solve the first part of the lab. What we're going to do is that we have access to all of the breakout rooms, so we can go in and out of them. So the idea is that we're going to go through each of the rooms, asking if you have questions. But if you're stuck in something or you have a question, then you can leave your room to the main meeting, and then we either going to be there waiting for somebody to come and ask a question, or if neither Michele or me are there, you would have to wait a bit because maybe we are already inside another room. The idea is that you go out of the room, you tell us we have a question in room X, and one of us go into that room and see if we can work out the answer to your question. So if you have any question, you just write it in the chat now about the dynamic. If not, I would let Michele explain the first exercise if he is ready.
Yeah.
Okay.
So the first exercise actually is to create a model of our DC motor driving a load without a gearbox. So in this exercise, you should use the Simulink blocks in order to, in essence, create the transfer function of, for example, the electrical dynamics that we saw and of the mechanical dynamics, and you should connect them in order to have a voltage input. So we would like to feed this motor with 2 kind of inputs. One is a constant voltage input, V, with 10 volts, and the other one is a sinusoidal input. You can find in table 1 the parameters of the motor, the nominal voltage of the motor is 48 volts. That will be anyway. We don't care, because we will, in case we give the input voltage, we will give the constant input at 10 volts. Then you have the resistance of the coil, 1.16 ohm, the inductance, 0.33 millihenry, and the torques and speed constant, the rotor inertia, and also the damping at the motor side, the friction, viscous friction on motor side, and is missing the damping at the load side. And we have also the no load current, which is related to the friction, Coulomb friction torque, as we saw in the lecture. First, build the implement the transfer function between voltage and position and velocity in Simulink using the Simulink blocks. You can use the transfer function blocks and the gain blocks to and the summing blocks in essence, and one integrator blocks. And once you have connected everything, you should provide the input voltage of 10 volts and see how the voltage, the steady state operating point is. This means that you will see that the load speed will start to increase. In this case, since we have no gearbox, the load speed and the motor speed are the same. So when you apply the voltage from an initial state of zero velocity and zero position, you see that the speed will start to increase due to the acceleration given by the current that flows into the coil, and then at some point as the speed will reach a steady state speed. This means that the motor keeps rotating at a constant speed. So you will see that at the end of the simulation, you will see that a plot of the position that will be kind of like a ramp, while you expect to see a plot for the velocity that is like a first order system. Then you should plot the voltage drop on the resistance to see that, and on the back and compare it with the back EMF, showing that most of the voltage it's actually going in the back EMF because we have a very little, we don't have load in essence, so very small current apart from the starting up, apart from the initial current at zero velocity. And then you can set a sinusoidal voltage and see that the with a bias, so a sinusoidal voltage not oscillating around zero, but around a certain value, for example, 10 volts. And you see that the rotor of the motor starts to spin up and oscillates around an average speed. And how to compute this average speed? You remember that we explain the moving average filter. So you should implement a moving average filter, and you have several ways of doing that. And you will see that autoregressive version that is correspondent to the recursive formulation we explained. It's the best one, because the other one will block your simulation because of computation time. And see after the filter what is the value of this average speed the rotor oscillates about. Then after you've done so, we will discuss together the results and follow with the next exercise. Okay, Octavio?
Okay, so I will create now the breakout rooms. Let's see. So let's create 9 breakout rooms with between 2 and 3 participants per room. So I'm gonna create them. Okay. Okay. Open. And you should all have received a notification now. Okay. Okay. So let's wait about 15 minutes, I would say, just to give them time to read the exercises, and then we can start going in at 5:05 if you want.
Okay. In the meanwhile, how do? We join one room at each time.
Yes. So let's do like this. You start from room 1 to the center, and I start from room 9 to the center. So there's one room with only one person.
Room 1, it's because one was myself.
Because okay, so let's move somebody from another room. And there should be another one with me. Let me just go to room 4, and I'm gonna ask. I'm gonna tell them that I'm gonna move somebody from that room because there's one room with one person. Okay.
Okay.
Um, hello, guys. Can you hear me? Kick me out of the. Can you make me host?
Sorry.
Can you make me host?
Host again. Yes.
Yeah, because it kicks me out.
Okay.
Okay. No.
Yeah.
Okay, now I'm host. Then I'm gonna go to that room that has 4 people. Oh, yes, I'm gonna join this one. Okay, we need to find a way to make them, to allow them to share the screen in the room.
I'm sorry, Professor. Can you hear me?
Yes, I can hear you. I don't know if maybe if Professor Fox can hear you. Can you hear Eliana, Michele?
Yeah, I can hear Eliana.
I'm with Danilo Luca Melis, but I cannot talk to him. So I change the computer. Can you put me with?
Okay,
Well,
roommate. I do it. Roommate. Okay. Good. Yeah, we need to make practice with this, but
yeah, it's I mean, it's the first time we did it, so there are hiccups along the way.
so now you go in room 8, Octavio. You.
I'll go to. Well, there are now 4 people in room 8. No, because that's Eliana. Okay. Yeah, I can go there, but let's wait another 5 minutes because we said 5:05.
Okay.
And I would say that at 5:45 we can close the room and then ask like depending on what we see. So I'll do 8 to let's say 5, and you do 1 to 4, and once you're done, once we're done with the thing, if it's too if it was too fast, then we wait until 5:45. What do you think?
So it's for one exercise, I think is too much, but
You mean for, I mean, when you say exercise, you mean all the modeling section, or you mean?
No, just M1. I'm talking about M1.
But I would say I would say we can give them the chance to try to solve the things themselves, right?
Sorry?
We can give them the chance to try to solve the things themselves. I mean, depending on after our round in the rooms, we see how things are going, and then,
Yeah, I'm saying, when do we start to do the round in the room?
you think 15 minutes is too much? We can already go if you want.
If they have questions.
Yeah, okay. But if you can, we can already start going into the rooms.
Okay, I
Okay.
start from room 1.
Yeah, I'll start from room 8.
And
Okay.
stay there a few minutes, and then we can go to the next ones.
Yeah. Okay.
Excuse me, Professor.
Yes.
So I have downloaded the folder from Dropbox, and I have already set up the path file, the path on the MATLAB.
Yeah.
But it still doesn't recognize init-m. So
Actually, you don't really need the path anymore. I changed my mind. I forgot to remove that. You could directly run init-m alone. Just open it with MATLAB and play it. So there is like a run play signal. If you open the init-m.
Just a second, because it keeps opening MATLAB on the wrong drive. Why? Oh, all right. All right, I'm seeing things, so that's an improvement. Do I have to open that script as a live script, or?
Open the script as normal script, like just double click on that, and
Yes.
then you have a run on the home ribbon, on the on the editor ribbon.
All right.
And then you run the script. This will load this into the memory.
Yes, the workplace is all filled with.
Okay,
data, so.
now you go to the model folder and open, and then these are the solutions already, the Simulink file with the solutions. So
Can I share the screen? Just a
yeah,
second.
sure.
Oh, I can't.
Wait a second. Are you Eduardo or?
I'm Johnny.
Johnny. How can I allow you to share screens? I try to activate for everybody. Participants, okay. Maybe I need to get out from the room.
Well, in the meantime, what do we have to start the Simulink now, right?
Yeah, exactly. Exactly.
Simulink here, I think. All right, I guess I have to use a blank model.
Yeah, blank model, and then there is library browsers to get the blocks. I mean, there should be a little, should follow the little tutorial that I put on the assignment that explains you how to load the blocks. But yeah. So in the library browsers, there are the all the possible blocks, like for example, on the left in continuous, you can get the transfer function block.
I don't think I'm saying the.
Under Simulink. So in simulation, in simulation tab, library browser, open it, and then you have Simulink as main file, and then you get continuous, and you have many blocks there, and one of them is transfer FCN, transfer function. And then you have also sources, where you can find the sign input and the const input. And then you have math operations, where you can get the sum block. And also
the transfer FCN.
Yeah.
You can just drag and drop it.
Yeah. Or double click, add block to mod or to the model. Yeah, I'm trying to check if I can enable you the thing, the screen sharing.
Mickey, make me co-host again. It kicked me out. In both of the accounts. That way, if it kicks me again, at least I have a backup.
Okay. Should host again. Yes.
Okay.
So I want to give the participants the possibility to share.
Yeah, I was asked again. I don't know how to do this. Let me look online how to do this.
Yeah. So, Octavio, just a question. If I say something here, everybody listen to me?
No.
No.
There's nobody's listening also, unless if they move into this one. The other thing is that if you want to send a message to everybody, then in the breakout room menu, there's one button that says broadcast message.
Okay.
Let's see, share in breakout room. You need to enable the option. You need to enable the option in your web portal. Oh, wait! I think that you can go inside the room and click on security, and then enable participants to share screen.
Sorry, can you repeat?
Let me try to do it myself. Okay. I think now they should be allowed to share screen.
Okay.
Maybe go back to the ones that requested you to do it and ask them if they can do.
Okay. Yeah. I got a few questions in other rooms now. Grassi and Rigoni.
Okay. Where was the room where they asked you if they could share the room?
Room 6.
Okay.
Rigoni. I don't know.
Dorigoni, no?
Dorigoni, yes.
So do you want
Rigoni, yeah. I go to room 6.
Okay. Okay.
Salve professore.
Sì? Yes?
Okay, we had some questions. First of all, we noticed that we have.
Sente?
Yes?
Mi sente?
Sì.
Should we speak in English or in Italian? Just.
Whatever you prefer.
Ah, ok, allora
Mi
andiamo
sente?
in italiano.
Sì. Chi è che parla?
Sono Grassi, Alessandro.
Ok, non parlate insieme, fate uno per volta. Vi sentite?
Sì, sì.
Ah, ok.
Quello che volevo chiedere era che nella cartella che mi ha scaricato c'è anche modello. Io non ho ben capito se dobbiamo usare il M1 motor come base oppure se dobbiamo crearci tutto il sistema da noi da zero.
Allora, M1 Motor, cioè, quelle sono le soluzioni, quindi l'idea
Ah,
è
ok.
che lo facciate, proviate a farlo da soli
Mhm.
e poi vediamo la soluzione insieme e poi partiamo dall'M2 Motor, cioè implementare la soluzione successiva partendo dalla soluzione precedente, fondamentalmente. L'idea è che facciate da soli per
Ok.
provare. Poi useremo eventualmente quei blocchi precostituiti per fare gli altri esercizi. Cioè, quelle sono le soluzioni fondamentalmente.
Ok. E noi usiamo gli appunti quindi come base.
Sì,
Ok, ok.
sì, provate da soli prima, poi dopo quando fra un po' farò vedere la soluzione io e andremo avanti.
Ok, i tempi più o meno quant'è che abbiamo?
Ma su 15, altri 10 minuti, poi inizierei a passare all'esercizio successivo. 10-15 minuti, insomma.
Ok, ho capito. Grazie.
Ok?
Grazie.
Okay, so room 8, they did not manage to install MATLAB yet. I cannot hear you, Nikki, you're mute.
Ok?
Yeah. So, I mean, I'll wait for them to install it and then I'll come back in a while.
Okay, yeah, I'm doing I'm solving dots and writing on the main chat in the meanwhile for everybody.
Okay. I'm gonna go to room 7. Did you already went to 1 through 6?
6, yes.
Okay, I'll go to 7 then. Nikki,
Yes.
can you make OAVM0 also host? Because I don't know why my Linux computer is kicking me constantly out. So whenever it kicks me out, at least I have this that can make me host. I can make myself host again without having to wait for you.
Okay. How is called?
OAVM. It's the only one that it's in this room that it's not OVRL.
Okay, okay. I finished the message and I do it.
Okay. Okay, great. Thanks, Nikki.
Okay, you're welcome.
No, I cannot make myself co-host. Can you make the other one as well host? Just in case one or the other, I lose one or the other.
I did it.
Yeah, what?
Co-host.
Wait. Yeah.
Yeah.
Okay, great. Now I will try with the other one to see if this one doesn't kick me out. So I'll go to room 7 now. Hi, hi guys, can you hear me?
Hey, yes.
Okay, how is it going? Do you have any question? How far are you in the exercise?
Now the point is that we never used Simulink, so we are trying to figure out how it works.
Okay,
Yeah, we are putting the data inside the model.
okay.
Okay. Now I have just an error on the electrical subsystem.
I think, by the way, I think you can share screen in case you want to share with your partner, with your colleague, the screen. I think I just allowed it. I because this is the first time we didn't know it was not allowed by default. So if you want to give it a try, just for me to see that if it's actually working.
Salve.
Salve. Allora, dov'è che sono le impostazioni qua? Quelle di simulazioni.
Ah, giusto, ok. In teoria in basso a destra c'è il coso per
Di solito c'era l'ingranaggio,
Sì.
ma non ce l'ho. Aspetta, ok.
No, no, lì. Ok.
Cos'è che diceva? Step size constant?
Fixed step size. Solver. Ok.
Automatico?
E cos'altro c'è?
Oh,
Ah, non lì.
No, non automatico, dovete metterlo
devo
TS,
mettere TS?
sì, T_S che dovrebbe essere stato selezionato nel file init.m.
Ma noi usiamo il file init, quello già fatto?
Sì, sì,
Ok.
sì.
Poi in realtà ci sarebbero anche gli altri file, cioè che non
Gli
dovremmo
altri
guardare.
file sono le soluzioni del...
Sì.
Cioè in realtà dovreste fare anche il file init, ma per semplificarci la vita usate quello lì e cercate di fare i blocchi Simulink, perché sono tanti esercizi. E, i prossimi esercizi magari se non avete finito potete utilizzare la soluzione dell'esercizio precedente perché sono incrementali, cioè ogni esercizio seguente usa i blocchi dell'esercizio precedente fondamentalmente.
Ok.
Ok. Hey, everybody, can you hear me?
Yes.
Okay. Now let's go back to the solution. We will quickly see together how to do the exercise. So first, let's review you see here the init file. We have all the relevant parameters that we have in the table. We can compute the mechanical constant. Note that to evaluate a single line, you can select it and press F9, and this will evaluate the value, for example, of the parameters. This way I evaluate this block, and this way I evaluate the mechanical constant. We see here the mechanical constant is 0.13 seconds, while the electrical constant is 0.28 milliseconds. This means that this is the one that limits our system. For the Shannon theorem, we can compute the settling time of the mechanical dynamics, and the bandwidth is 1 over the settling time, which is 878 hertz. Then, to be conservative, we use a sample. If we should use something that is 10 times higher, so 8,000 hertz, and this corresponds to, for example, with a certain rounding, to a sampling time of 0.1 millisecond, so 10 to the power of -4 seconds. And we have here the parameters of the load. We don't use them now in this exercise. And this is the supply voltage, V bar, and the values of the sinusoidal. This is the amplitude of the sinusoid, the frequency of the sinusoid, 1 hertz, and this is the offset, the bias, yes, the offset. So if we want to design this system, we have the library browser on the left, and our system on the right, an empty Simulink simulation that you create with new. And what we need is the transfer function block. Sorry. Okay. What is needed is the transfer function block. That is a continuous transfer function. Is you have in continuous. Then you need another one for the electrical, one for the mechanical dynamics. For the electrical dynamics, we unfortunately in Linux things disappear all the time. And we need to set the numerator and the denominator of this, and the numerator is 1 and the denominator is L. This is the coefficient of the S variable and R. And if you do like this, you get this, which is the electrical dynamics, right? For the mechanical dynamics, you have one at the numerator, and at the denominator you have the inertia of the rotor of the motor, and the viscous friction of the motor. That's it. We have the mechanical dynamics here. Then we need some gains, because we have that the output of the electrical dynamics is the current. We need to multiply by what to get the torque, the motor torque, you remember? We need to multiply by K, which is the torque constant. Since we already ran the init file, we have all this in the workspace, in the memory, so they are accessible. Then the motor torque, let's say we have no load, goes to the mechanical dynamics, and as output, what do we have? We have the rotor, the motor speed. So if we want to have the position of the rotor, we put an integrator, and we get the motor position. Then what about the back EMF? to the input. Let's say our initial input is a constant input, v bar. And this voltage input is given to, it needs to be subtracted with the back EMF. So we put a summing block here that you can find in the math operation here. We have a, sorry, we have a plus, but to make it a minus, you double click on that. And you put a minus here. This becomes plus minus block. And this is the input to the electrical dynamics. But if you right click on the thing, it will copy the block. If you do Control R, it will rotate. And this torque constant will be the same as a speed constant and should be multiplied by the motor speed. So the motor speed is here, is multiplied by K. We get here the back EMF, and that's it. So this is the system. We might consider for later another the other input, that is a sinusoid. Here, what are the input? The parameter of the sinusoid are, for example, the amplitude AV we discussed, BV. I cannot find AV in memory. A underscore V. Ah, okay, because I didn't run this yet. I just ran the thing blockwise. Okay, I run it. And now I'm fine with that. This recognizes AV and BV. The frequency is FV. And as output, we need something to plot. And what we plot, which makes Simulink very appealing, you can find in sinks, and it's called scope. And scope, you just link to the variable you want to plot. And this is the motor speed or the motor position. And that's it. You're done. Then you go in modeling, you play, you run a simulation, and you get the plot. So this is a plot of the speed. You cannot see much, so it means that the simulation is too long for the electrical dynamics you're trying to see. And so you can change the stop time to, for example, setting to 1 to magnify this effect, which is the starting up. Remember to set the in model settings. You should set fixed step or the 4 solver and set our sampling time TS that we computed before. Otherwise, Simulink will do it automatically, find the best one with a variable step solver, but this is not good for what we see later, that is the sensor quantization problem. So now modeling 1 second is still too much, maybe 0.1. And with 0.1, we can see the speed that goes to the steady state value and the motor position that after an initial acceleration goes to constant velocity. Now, let's keep these values on top and verify that these values, they satisfy the ones that we computed in simulation. Sorry, where is the MATLAB now? And the one we computed in the lecture, we expect to have a no-load speed of 160, and you see here that this is exactly the steady state value, 160.71, blah, blah, blah. No-load current, how much is the no-load current? It's the current whenever we have, we are going a steady state, so we need to plot the current. We didn't do that. We add a scope, right click, I drag and drop, and it just copy this, so you can do right click and copy and paste. And the current we say is here, motor current at the output of the electrical dynamics before the torque, and the current we need to, of course, we need to resimulate everything. And if you open the scope, motor current, now it's something like that. And the no-load current after the initial peak, you see that is around steady state value, and it's supposed to be 0.26, and is exactly matching with what we found by our equations. And the same for the no-load torque will be 0.01, that is just multiplying the no-load current time the times constant. So we miss one plot for the motor torque, that is here. We run again. 0.01. Let's see if it's straight through. Yes, 0.016. 0.016. Very good. Then we asked to put a sinusoidal input. So we replace this. We put our sinusoidal input here. We run again, and we see that we cannot see anything because the sinusoidal input has a period of 1 second, frequency 1 second. So we should, to see the sinusoid, we need to increase the simulation time. And now we see sinusoidals. Why the sinusoids are so small? Because I did an error. Frequency, sorry guys, this is an error because this is not frequency, but it's pulsation. He wants it in rad per second. So you need to multiply the frequency times 2 pi. So this is the wrong name for the parameter. But for historical reason, this is what we have in MATLAB. And now we have the 1/Earth sign that you see the speed goes around, oscillates around an average speed. How much is this average speed? We can do in many ways. In the lab instruction, you see that there is one way, one better way to do. That is, you remember the recursive equation we implemented, we explained in the class. Then if you pass this into the Z domain, let's say just replace the future sample with a Z times the Y variable, which is the output of our average filter. So this is the Y is the moving average that we want to compute, and U it's the input of our signal, that is the velocity. So if we pass to the Z domain, we get this transfer function, and this transfer function has a numerator. Sorry, this is wrong. This should be here. So numerator of Z 1/m that goes here without any known term, 0, and the denominator is 1, the coefficient of Z here, minus m minus 1 over m, where m is the size of the moving average window. And if we do that, and this is a very simple filter we can add to our system, and I already prepared that. I can take it. You see here, if you open it, you have a numerator and a denominator, and we need to put the speed on top of, as input to that, and the numerator and the denominator have this so this was this one in essence. We have a third way that is with the first order filter. So let's say we set a very big window, 20,000 samples for doing the moving average. We simulate, and we get something like this. It's still oscillating, but it gives us the trend. So if I want to filter even more, I need to increase the moving average size, window size. I evaluate again with F9. I change again. And I see this even smoother. So it's the average speed is going around under 40 rad per second. Finally, we want to measure the one question in the assignment was to check what was the drop on the back EMF and on the resistor. So I just copy from my solution that. So the back EMF, it's this one. And the voltage drop is current times resistance on the resistor. And we see that the majority of the voltage goes to the back EMF and very little on the current. Why? Because we don't have load. So we are just to overcome friction, viscous friction, and at the steady state. Then let's go for the next assignment. You can save it if you want. I suggest you to save it as a MDL file rather than another extension, which is SLX. You can even save it in previous version of MATLAB to be able to open it with older MATLAB version, older Simulink version. And the next exercise, it's about adding a load. So now we have the motor spinning at full speed, but we want to control a link with this motor. So we add a load that is just a rotating rod of 0.15 meter, 15 centimeter, a mass of 0.2 kilograms. This rod is rotating in the horizontal plane, so there is and is attached to one endpoint to the motor, and so there is no gravity because it's moving on the horizontal plane. It has some viscous friction, so this time we have this viscous friction also at the load level, and we want to see adding a load how the time constant of the system change, and try to add some load torque on the load. And whenever you add a torque or a load and also a load torque, you will see that your operating point, which is the steady state value that correspond to a certain couple of pair of torque and velocity values, will change and shift along we remember the motor characteristics curve that we studied in the class, and And we want to see how these operating points move. We expect that it will move at lower speed, and check the new values, steady state values of motor torque, compare it with the previous exercise. So Octavio, if you wanna start again, the break rooms.
Yes. give me one.
Room, I can do that. I can do that.
Okay. Just to verify that you're not assigned to any room, so then I'll rearrange the rooms when they're done.
So how long we this time we can be faster? Let's
Yes.
say,
Let's give them about 5 minutes.
yeah.
Maybe I'll go. Well, no, I'll give them 5 minutes. I'll start again. Maybe I can start from 1 now, and then you can go from 8.
I suggest that they ask. They have a way to ask us to enter the rooms.
Is there? I mean, I told them they could come out of the room. And
No, they were. I mean, they were calling me from outside, from inside.
Okay. Okay, good. Then
Yeah, I don't think we didn't need.
okay, so that's fine. Probably they will call you. So if you're busy, you can send me to a room. Just send me a private message, and
Yeah.
then I can go. Give me 1 second, Nikki. I'm gonna get the pen of my surface because I wanted to explain an equation to the guys and I couldn't find a way, so I'm gonna get a pen so that I can share the screen and write on the surface.
Okay.
Okay, I'm back. I think that for the next exercise, an important thing to say that I think they're gonna have problems is to derive the equations of motions of a rotational object based on Newton's second law. And then you need to, it's the torque equals the rotational inertia times the rotational acceleration. But then you need to derive how the rotational inertia is well, not derive, but just write down the expression for the rotational inertia.
Yeah.
Because, well, probably a lot of people don't remember those things or don't have it at the top of their head.
Yeah. Anyway, we'll see this later in the course.
Yeah. I think that.
Okay.
Okay.
Let's go back. Okay, are we back? Can you hear me?
Yes.
Okay, so now let's try to solve assignment 2, which is adding a load. And adding a load, what does it mean? Since we have no gearbox and no compliance, it means just to sum up the values of the inertia and friction, viscous friction of the load, of the rod we added. So we have the parameters of the load, let's say 15 centimeter length ml. And if you remember, we will review this in the dynamic lecture, the inertia of a rod, a mass decentralized rotating around one of the edges is 1/3 length of the rod squared times the mass. And this is just an equation that comes from the parallel axis theorem. We will see that. And this is the friction coefficient of a load. And then, so what we need to do is to change the inertia, adding this load. So we go into the inertia part of the mechanical dynamics, and we sum the load inertia and for the friction we add the load friction. Okay. Now we simulate. We go back to the previous constant input. Sorry, I lost that. Sources constant. I drag it in. V bar. We simulate, we expect a similar behavior, but the value of the steady state velocity is slightly lower because we added some friction on the load side and it's about 159.7. So if we want to verify whatever we computed in the class, the no-load speed is computed this time from the motor friction plus the load friction. And we see that is 159.7 as the simulation tells us. Now, what else? The assignments also ask to, so if we set the friction BL to 0, and we simulate again, we should go back to the previous value. That was under 61, I think under 60.7, blah, blah, blah. Very good. Now, we don't care much of this. We want to drive a load. We want to perform some torque on a link. So we need to consider this load force. And since we have no gearbox, we could subtract here, as in the mechanical equation, and we have math operations, sorry, summing block. I think it's something like this. Yes, very good. So we have our motor torque.
Maybe you should explain what you did in the.
So now we are trying to add a load torque. So the load torque is added, subtracted from the tau amp. If you remember the slides, the motor torque.
What I mean is what you did in the block, because you did it a bit fast, like to rearrange the signs.
This is to rearrange just the plus and minus in the summing, and then you with Control R you can rotate it. Control R rotates the block, and I never understood what this means, but I think you can have different orientation of the plus and minus sign. You should read. You should read the instruction. Each function, each block in Simulink is properly documented. You can find a lot of resources. So let's say we have a constant load. Now I don't know, 2 Newton meter, and we subtract this load, and what we expect is that our rotor will go to a lower steady state speed. Actually, is too much. Let's say 0.1, 0.2 Newton meter. So the load torque I set was so high that it was reverting the motion. Yeah, and this time the motor starts to spin up and reaches a steady state velocity where friction is compensated and the load torque is balanced. Okay. Very good. Now the third exercise is to add a friction, introduce a gearbox between the motor, electrical motor and the load. And this why? Because we have a very high velocity, 100 rad per second. And if we plot the torque, we see that is quite small. So we would like to achieve so torque is around 0.3 Newton meter, 0.5. So it's very small. We would like to amplify the torque and reduce the speed. So we would like to put a gearbox in the middle. But since the gearbox has no compliance, no elasticity involved, we should change the values of the inertia of the motor and of the friction on the motor load side to account for the gearbox presence. And do you remember how to do that? You remember that the gearbox has the effect to amplify the inertia of the rotor whenever you go load side. So let's have 5 minutes more to do that, or a little bit more, and go back in a few minutes.
Okay. I cannot see you because you're muted.
Yeah.
Well, maybe this is not the right place to discuss it. I want to ask you a question about what Matteo asked in the group, but maybe we can talk about it later. Did you see?
Yeah.
Okay, maybe we can talk about it later.
Okay. Your voice is a little bit not so clear.
How about now?
Yeah, a bit better.
Okay, let me try to fix it. How about now?
Yeah.
Is it the same or it didn't sound very similar?
Slightly better, slightly more open. It was like closed, like
Okay.
not close. Try to speak close to the microphone.
No, I think I was using a different driver because Zoom by default chooses some specific
I see.
microphone.
Okay, let's go back.
Okay.
So let's see what we need to add a gearbox. First, we should decide how much is the gear ratio. And you remember for the slide, there is like an optimal value for the gear ratio that is square root of the load inertia divided by the motor inertia. Let's see how much is that. Calling F9 to evaluate, and it's around 10.5, so quite small gear ratio. And now we should compute what is the equivalent inertia of the motor reflected to the load. And we saw that you should multiply by n squared plus the load inertia. So the new load is J equivalent, and it's like this, and the same for the viscous friction. Then whatever we need is to replace this inertia with Jx and friction with Bx. We already evaluated. Plus, what do we need? This is the load. This is the motor torque. You remember? We need to increase. To get the load torque, we need to multiply the motor torque by the gear ratio. And what else? Back EMF, motor speed. This is no longer the motor speed, it's the load speed. So to get the motor speed, we need to remember the load speed is much smaller than the motor speed. We need to multiply by the gear ratio. Because whatever we multiply for the speed constant to compute the back EMF is the motor speed, not the load speed. So now we should be able to simulate. And what we want to do is to compare. Let's remove this for now. We want to compare the speed, the motor speed, and the load speed. And the motor torque with the load torque. Sorry, this is an error. Should go before. This is a load. Okay. Motor torque was low and load torque was up. Okay. Oh, this was not happened here. Didn't work. Okay. Okay, again, we have a very long simulation. Let's put shorter. You see here, the first signal is always the yellow one, is the load speed, and is way smaller, 10 times smaller than the motor speed. While at the torque level, we have that the yellow signal is the load torque is 10 times higher than the motor torque. There is an optional exercise that if we want to add compliance, and we want to model elasticity into the system. And in this case, we need to split the two dynamics, because now the load dynamics, the motor dynamics, mechanical dynamics is separated by the load dynamics by mean of a spring. You can check this for exercise to see how it works. But the next exercise, it's about introducing friction, specifically Coulomb friction in the model, and this Coulomb friction we can compute from the null current situation. So you get that from the data sheet, and you multiply by the torque constant. And the viscous friction is already considered in the terms of BM and BL, motor side and load side. And this time we try to give a sinusoidal input that crosses 0, because we want to see the effect of Coulomb friction. And you know that we see that only whenever velocity is 0. So if we oscillate with a sinusoid around the velocity and the velocity never gets to 0, you won't see Coulomb friction. So we need to see a change in sign in the speed to visualize the action of the Coulomb friction. You might need to reduce the sampling time to better visualize that. And you want to see how does it affect the load velocity, what happens in correspondence of the crossing points, and try to increase the Coulomb friction 5 times and see how the speed variable is changing, its speed plot is changing. And yeah, plot the motor torque together with the motor speed to see this. And the Coulomb friction you should add should be at the motor level, not at the load level, because then it's amplified by the gear ratio. Yeah, sorry, this is the solution for later. And the Coulomb friction, for the Coulomb friction, you can use the block. There's a Simulink block just for that. You can search for a block and you see Coulomb and viscous friction block. And this has the parameters of Coulomb friction, and you should put tau C and the viscous friction. So let's do this exercise and come back in 5 minutes.
Michele,
Yes.
maybe remind, I mean, and you said about the extra exercise. Didn't we say that this, didn't you mention in the first lecture that the extra assignments were for the...
I don't hear you. I hear you very bad.
Okay, can you hear me now?
Now it's better. It's
Okay, so didn't you say in the very first lecture that the extra exercises in the labs would count for the LODEC?
Yeah.
Maybe just remind them when they're back from the exercise that just tell them, like, I remind you that if you do the extra exercises.
Yeah. I agree. I need to delete immediately from the folder. Okay. So let's see how to implement friction in our model. Coulomb friction. First, we evaluate the friction torque, tau c, and we see it's around 4.2 millinewton meter. We are talking about of Coulomb friction at the motor level, so it's quite small. And now we introduce the block, the Coulomb friction block. If we look at the option at the documentation in the block, it says that the x, that is the input, it's taking the sign of the input. So if we put viscous friction to 0, we will have sign of input, which is the velocity, should be the velocity because Coulomb friction is opposing the motion, times the offset. And as offset, we set tau c. Then, so we provide motor speed as input, and this Coulomb friction, it's going to reduce the amount of torque available from the motor to reduce the motion. So we need to subtract this Coulomb friction to the motor torque, so with a minus, and then go to the load. Now, if we give a sinusoidal voltage, we said that we want symmetric voltage. So let's double check if our bias is 0. No, it's not 0. So we set it to 0 to have a symmetric sinusoid around the origin. We simulate. You want to look at the speed of the motor. Okay, still we are looking at a very small time window, so let's increase to 10 seconds. Okay, there is no such a big difference. You see here a slight change in slope. So this friction torque it's not able to stop. Is changing the slope of our speed. So let's try to increase the value of tau c 5 times. Tau c 5 this and F9 to evaluate. And now we can see now that at the cross we have that the motion stops, and before it's like a dead band. Remember, it's stopping and starting again. So the next exercise, now that we introduced Coulomb friction, it's about computing efficiency. And let's do the following. Let's do M4 and 5 together to speed up a bit. So you remember that efficiency is computed as the mechanical power out that produce the motion. So it's speed of the motor times torque of the motor minus Coulomb friction, because Coulomb friction doesn't produce any motion. So mechanical power out over the electrical power in, that is voltage times current. Again, we consider a sinusoidal voltage, and to have we want to see that the mechanical power, we also want to compute both efficiency and mechanical power and electrical power. So we want to plot all of them, and we want to see that we have an inversion of the motion at 0 velocity, and whenever the mechanical velocity goes to 0, also the mechanical power goes to 0. And there is a trick, because you might have also that the efficiency spikes to infinity whenever the electrical power crosses 0, because electrical power, if you give a sinusoidal voltage, it will be a sinusoid as well. So you need to take care of this. Let's say we will see how to do that in a way. And negative, you can have negative efficiency if you have, for example, some velocity of the load, and you have a different value of mechanical power and electrical power. This means that the motor is generating electrical power from the load motion and is acting as a generator. That you could have that the motor sometimes does this, especially when there is an external gravity applied to the load that makes the load move externally. Ideally, we want to maximize efficiency, which means minimize Joule losses. And we know that the worst situation is when the motor is in a stalled situation, where all the voltage goes into current to, for example, overcome, create a load torque that is too high, so there is no motion. In that case, all the current, the maximum, all the voltage drops into current onto the resistor and is wasted there's a big waste in terms of Joule losses, because there is no mechanical power output, and therefore the efficiency goes to 0. To emulate this, we can add a spring on the load, because if you add a spring on the load, that will compress as the load moves, the force will increase, and you arrive at a point in which you have a load, exactly the load torque that equilibrates, for which there is an equilibrium with zero velocity. So just a hint. Take also some. Let's come back in 15 minutes, and you can do a small break as well. And let's discuss again the solution at 35, 45, at 10 to 7.
You forgot to mention about the extra activity. Also, Michele, this is going to be recorded, so hopefully people will hear it. But just before you,
I don't hear you, Octavio. Change the microphone.
can you hear me now?
Yes.
Okay. So 2 things. You forgot to mention about the extra activities of the lectures.
Yeah.
And the other thing is, before you finish, this is going to be recorded, so hopefully people will hear it. But just before you finish, just allow me to tell them to install the virtual machine. I will just share my screen to show them how the announcement that you placed on Moodle, so that they can download the virtual machine for tomorrow's Python tutorial. And then I will send instructions to install PyCharm inside of the virtual machine.
Okay. Yeah.
Ciao.